Hey guys, welcome back. This is day 8 of Advent of Code 2025. Here we're given a list of 1,000 points in 3D space. So X, Y, and Z or Z for each point. And yeah, there are 1,000 of them or so. And the problem is well, first they want us to connect the pairs that are closest together. So the 1,000 pairs that are closest. And then that will form like clusters of points in 3D space. And then they want us to count up how many points there are in the largest 3 clusters and multiply those 3 numbers together. And that's the answer to part 1. So I'll walk you through that. Perhaps I'll just start by drawing out some points. This is 2D, not 3D, obviously, but you'll get the idea. So we've got all these points in our input file. And then they want us to connect the closest pairs, the 1,000 closest pairs, and so the closest pair here might be this, or it might or this, right? And then so you keep connecting, right, until you've got the 1,000 closest pairs, and then you end up with these clusters, right? And they want us to multiply the 3 largest ones together, or the sizes of the 3 largest ones. So here, this would be like 1, 2, 3, 4, and here it'd be like 1, 2, 3, 4, and here it'd be like 3. And then you multiply those numbers together and get an answer, and that's what they want us to output. So it's 1,000 points. So that's many more possible pairs, right? If you have 1,000 points, that's about 500,000 possible pairs, and then we want 3 clusters, the 3 largest clusters that form as a result of pairing them, right? And then get the sizes and multiply them. So let's look at my code here. So here I'm just importing the data. I'm turning it into a list of lists. Each sublist is a point, right? Showing the first 3 points here. And then here I'm calculating all the distances. So for each pair of points, looking at the distance between the points, right? And I'm using basically Pythagoras theorem here in 3D. And this is technically the square of the distances. You could take the square root to get the actual distance, but since we're just comparing distances, we don't actually need the square root. So so it ends up being a list of well, it's actually a dictionary, right? With where the key is a tuple of the 2 points, and then the value is the squared distance, right? And here I'm sorting by distance, and so the edges variable gives us just the pairs of points that are closest together, or actually all the pairs sorted by distance, right? And then edges 1,000 gives us the first 1,000, right? So I'll show you 2 solutions to part 1 here. One is based on a graph, and then the other one is based on something called union find, which I'll show you in a minute. But let's start with a graph solution, which I think is a bit more intuitive. So we'll create a graph variable and set it to default date of set. Right, so the keys in this dictionary will be points, right, like nodes in the graph, and then the values will be sets of points, right? So all the points that are connected to the point in the key, right? So we're going to do for I, j in edges 1,000. And we're going to do graph I.add j and do the same the other way around. And that basically builds the graph for us, the graph of like connected points once we've done the 1,000 connections, right, to get all the pairs. So let's have a look at the graph here. So for each point here, this is the 90th point, right? This is the 610th point. We have all the other nodes that are directly connected to all the other points that are directly connected to it, right? And we've got a total length or total number of 856 points in our graph here. Now we just need to find the clusters and their sizes. So we're going to look at all the points in the graph and keep track of which ones we've visited. So I'll create a visited set. And if the point is in visited, we're going to continue. Otherwise, we found a new cluster here, right? So new cluster, and we're going to explore the cluster with depth first search here. So create a stack variable here, and I'll put the point in it, and then while stack, we're going to, pop from the stack, so I'll call it node, and then we're going to look at all the neighbors of node, right, using the graph we just built. So I'll do also, let's keep track of the count of the number of points in each cluster. So count equals 0, and then once we've popped from the stack, we can increase the count, and we can say that we visited the node here. So visited.add node, and then for neighbor in graph node, if we haven't visited the neighbor yet, then we'll add it to the stack. So if neighbor not in visited, then visited.add neighbor, and stack.add neighbor, and then we'll keep track of the cluster sizes. So create a list there, and let's see, when we're done with the stack, then we can add to our cluster sizes list. So cluster sizes dot append count, right? And this should be append. Whoops. There we go. And then let's print out cluster sizes. Let's see if we get the right thing here. Okay, so we've got all these clusters, and we want the largest one, the largest 3, and then multiply together, right? So sorted, and then the last 3, which is this, and then we can do math.prod of those to get the answer. So that's it for part 1, or that's the first solution to part 1 here. Another way to solve this problem is with something called union find, and I've got the code for it here. So this also produces the right answer. I won't go into too much detail here, but you can Google it or pause the video and look at my code and try to figure it out. So it's called union find, or sometimes disjoint set data structure. So I'll let you look into that if you're interested. I'd forgotten about this, but it turns out that this is a good way of solving this particular problem that we're looking at. So I'll skip over that now, and we'll move on to part 2. For part 2, they want us to keep connecting closest pairs of points until all the points are in one cluster, basically. And for the last pair, we're supposed to get the x-coordinates and multiply those together. And that's the final answer for part 2. So let's work on that. I've created this helper function here, which does a depth first search of a given graph starting at a particular point, and it returns how many points basically are in a in a cluster that contains the initial point here. That's the first argument. So basically the approach here is to create a new graph, and let's do default addictive set, and then we're going to add edges basically one by one. And now we're not doing the 1,000 closest, right? We're just doing as many as it takes to connect all the points, basically. So for I, j in edges, remember that was the variable we defined up here, right? So edges is all the pairs basically sorted by distance. And so for I, j in edges, we're going to do graph2 I.add j, and the other way around. And then we want to stop when all the points are in one cluster, right? So basically if we're going to use our depth first search function here, if DFS of I graph 2, or we could use j here. Basically, we want to check that all points are connected to each other, so it doesn't matter if we start with I or j here. But if depth first search of I in graph 2 is equal to the length of the points, which is 1,000, then all the points are connected, right? And we want to look at the last edge we added here, so that's I and j. And we want to get their x coordinates, so we're going to just print points I 0 for the x coordinate times points j 0, and then we're going to break because we're done, and that's the answer for part 2. So I do want to note here that this is not efficient at all because we're doing a full depth first search here for every edge that we add. So it's not the most efficient solution here. There's going to be something more efficient. For example, I mean, if you use an approach based on this union find, you'll be able to do much better in terms of efficiency here. But this solves the problem for part 2, so I'll leave it at that. Thanks for watching. I'll see you in the next video.